Good. So do you remember how the old density of state looked like? Do you remember what was the value where the computed conduction bands ended? What was the value? Second? For where we ended the conduction band, conduction states, right? We saw the state being calculated, then a couple of peaks, and then everything went down. 10, right? Good. So the last value we computed last time was like a 10 eV in that density of state plot. Now with the new calculation, where we increase the number of bands from 60 to 160, right? Or was it 180? 180, okay. Now we end at more than 30 eV, right? So when we increase the number of bands in our calculation, we compute more of the unoccupied bands. Right, but apart from that, we still see that we're starting the density of state at somewhere around -3 eV, then we go up like almost like a square root. For a while, then come a bit more features due to the electron-electron interactions. It's not the ideal model, it's a bit more complicated. We still have the Fermi level, I think, at around 1 eV. We will check that in a moment. There is no band gap here, right? So that is clearly a matter. Let's do as we said and check the Fermi energy. Fermi energy is still the same, around 1 eV. So our calculations seem to be alright. Now we try to make Now we try to modify the DOS calculation a bit. So I copy my initial DOS input file, dos.in, to dos02.in. Then I open dos2.in, and the first thing I change is the output file. That should be different. If you have a lot of k-points, we can actually ask for a much more accurate computation to integrate the density of states in the Brillouin BZ sum, and we will start with T integration. Then we do not need to provide information of the broadening. Remember, the broadening factor is a parameter that we normally choose to facilitate comparison between computational result and the result of an experiment. For example, when we ask for the density of state of a valence region, we normally do photoelectron spectroscopy. The principle between PES and XPS is the same. So I bracket out the broadening factor. I also factor out the type of broadening, because I don't have a broadening. Then I try to rerun my DOS calculation, this time with DOS02. And luckily it seems to work. The calculation is more accurate because it does not depend on the broadening factor. It basically splits the Brillouin zone in a set of tetrahedrons. You know what a tetrahedra is? It's a geometric object that is defined by 4 points. Okay, I didn't do that very nicely. A tetrahedron, basically. with, let me try that again. It's so difficult.
Pyramid.
No, but with 4 sides.
Square
Like, do you remember the tetrahedral interstitial? That is a tetrahedron, right? So it is basically, it's a line like this, right, here, and a line like this, like inside this whiteboard. And then we have lines connecting them, like here's a line out like that. Okay, and you can basically split all regularly spaced shapes into sets of tetrahedrals, and then perform the integration of the density of states. Actually also make use of the high symmetry points, and you get a very accurate result. Now we plot those 2, and hopefully it looks good. Right. So nice. So this one looks pretty decent. Normally I could be right. Zoom in a bit. I think I want to have more points. So let's try that again. So, okay, now we are a bit more reasonable here, right? So we go from minus 10 to 10 eV again, and we decrease the step size to 100th. Right, so there's one more good advice. If you give the density of state in a report or paper, you don't want to have it look like this, okay? Not so spiky. You want to have it more smooth, right? So you have any success with your density of state?
I still didn't get the continuous line. It's just like on the table.
Okay, let's. Do you have many tables?
For here to I tried
999 tables. Can you show me your structure?
structure.
Yeah. With a lot of atoms, that is good.
Should I shut that?
No, you do structure optimization, right?
Yes.
Then just read. Okay. You use the primitive units, right? Do you also use the primitive unit set?
No, just
Conventional standard. How many electrons do you have in your calculation? Mm-hmm. 41. What kind of potential are you using? What pseudo potential are you using? 50 bands you have.
Bands 30 for to cell.
Okay, but which potential, what is 50?
Cutoff.
Cutoff energy. What's your cutoff energy? 49, okay. Which potential fire are you using?
SG.
Like when you 10, when you open your potential file, you have like the Vanderbilt code potential. Does it look like this basically? Do you use the lithium PVE version 1 USPP, or which one are you using?
I use SG.
Let's see.
In FQE and SG50.
Try the SSSP. That's what you're using?
No.
No. Try this one. So I would consider this at least a decently looking density of state, meaning my resolution is okay. It represents the physical properties that I expect in general, right? That is being a metal. Now there are a lot of peaks, but that is understandable. There are a lot of the electronic effects are not that simple. There is, the Fermi energy is still at around 1 eV. So one could in principle either leave this big peak here or try to reduce the energy range a bit. Because actually the further we go away from the Fermi energy, the less reliable our results will become. Let me try if I can cut it, maybe like this. More. So that kind of zoom range would be sufficient in my opinion. We still have the Fermi energy inside. F here. We see where the valence band region begins. We see the a sufficient part of the unoccupied states. Right? If you go much further, it's also not that interesting. At least when we are interested in the frontier states. Okay, so what else? The last example, maybe I want to show you what happens when we use only one K point. So first, right, my K points are definitely not converged. Second of all, the tetrahedron method will not work because it needs more than one K point in each direction. So first I run the calculation again. Submit a queue. However, the calculation goes now much faster, right? So okay. So the first thing I try is to run the DOS calculation with my tetrahedron method. And it actually worked. Unbelievable. Okay, let's look at it, because actually it should not work. Right. And that's how my result looked like. Right, so something failed here. Good. Definitely an error from my side, course, the tetrahedron method, as I said, needs more than one K point in each direction. So I go from my tetrahedron method to one of my broadening methods. I use the Gaussian broadening with like 0.1 Rydberg broadening factor. So I have this calculation, I look at the density of state now. I open the wrong file, because the result is now stored here. Right. And now I get a file like this. Does this look familiar? Okay. So here the thing is, do you remember that we got a lot of K points and each K point had like a lot of eigenvalues? The eigenvalues are different from K point to K point, right? So actually, when I have my first band, one K point will have a value here, right? Another one will be a value here, then will be another one having it here, another one here, here. 49 of them. I go to my next band, right? The same thing. I have a lot of points that are slightly in the neighborhood or in the near neighborhood of that peak, right? Adding up to that peak. And when I sum them all up, I will get a density of state that looks much smoother, right? So when you get a spiky density of state for a solid, probably you don't have enough K points. So what you would do is save the density of state, increase the number of K points in your SCF calculation, recompute the density of state, compare them with your previous density of state. If there are a lot of changes, repeat the process starting with increasing the number of K points. If your density of state of the new calculation and the previous calculation look almost identical, or they do look identical, you stop because you have converged your calculation with respect to K points. Shall we make a test? You try to check your DOS calculation with a lot of K points, let's say at least. No, I don't give you a number, you need to figure that out yourself, okay?
So we need like this.
No. This plot is not good.
Oh,
Give me a second, right? You need a plot as we had previously. So I had here like 999, and we can reduce the number of bands a bit because we want a fast calculation. We have 48 electrons, 30. So you want a density of state that is correctly obtained from at least from the computational part. If you have a metal like lithium and you get a spiky density of state, that might be not a strong indication that something went wrong. But if you have a band gap for a system that is a metal, then something messed up in your calculation, and you need to find the mistake. So, okay, let's figure out the DOS calculation. Let's look at the density of state. So you want a density of state that looks more like this. I reduced the number of unoccupied states a lot, right, to have a fast calculation. But if we look at the around Fermi energy, let's zoom in first. It's difficult to zoom in. Then we know Fermi energy is at 1. That looks roughly okay, that region. Okay. So what I would do next is I copy the recently computed DOS, that is DOS, total DOS.DOS, and I call that now total DOS.DOS, and then I like to indicate the number of K points I use, 999 for example, in the file name. So I copy that file there. Then I go into my lithium calculation. No, not the output, the input. I increase the number of K points slightly, let's say 13, 13, 13. I submit the calculation again. I need to wait a bit. I compute the new density of state, and then I compare my previous result with the new result. Right? The one with the 999 K points with the 13, 13, 13 K points. And hopefully they look roughly the same. If they look roughly the same, I would keep the number of K points fixed, add a couple of unoccupied states. So how is your density of state calculation doing?
I think I can type a listen to you, right?
It's difficult, right? But
Yes.
so I try to show you the pitfalls, but actually what I'm also interested in is that you show me that you managed to go from your spiky density of state to a density of state that looks correct, right? Because I really want to push a home assignment to you, right?
Teacher, is the capital letter or the small letter? Because I tried the SSSP, and this one is little F.
Yeah, little I have little one, yeah.
So do I have to change
No,
or
no.
just like?
It's just the file name. It could be whatsoever, right?
But I can run the file.
You can't find the file name.
I can run.
Okay, let's see. It's stopping. That line in name. So can you open the input file? Is it in step or in step? So something around there is wrong. Can you close here yes, this little sign missing at the end. And the comma. Yeah. Correct? And the comma at the end of the line. Yes. Save and try it. Okay, so here is my new density of state. See? Let's look at the old one. Old, right? Try to remember it. Let's put it maybe like this. Why don't you do this instead? Oh, you can't do that. So remember this. That's the new one. Do you see a difference? New, old. new.
It's more flat.
It's more smooth here, right, in that region. It was more spiky. So we could go to the next cape one, right? So 15, 15, 15. Okay, but maybe I do that. You focus on your density of state calculation, okay? I show you my result and then we fix yours, okay?
Can you tell me the TOS files?
What's the question?
I missed this part.
Yeah, that is the type of integration. So basically, when we compute properties, we go to reciprocal space, and then we want to integrate the whole Coulomb zone. So we want to make an integral over the volume of the Coulomb zone, compute electronic properties. But what we actually do is we go to the Coulomb zone and we make a summation over a couple of points. If we do the summation of a couple of points, that's not very accurate, right, compared to the integration. So what we do is we actually apply a broadening. So we don't calculate a point, we actually make a small Gaussian broadening of it, right? So we increase the range basically. However, that is a bit unphysical. Because you can't just go there and do some broadening and then say that is reasonable. Especially not with the Gaussian broadening. Then, to get a more accurate result, people figured out, oh, there's a technique called Coulomb zone integration. You take your Coulomb zone and you try to put it in smaller pieces. Right? Something like when you have a square, right? You can make it more simple, make it in a set of two triangles, right? And you can put these triangles to divide them on more triangles. As many triangles as you think of it. So, and you can do it with any shape, right? That has, with any n corner shape. If you take a shape that has 5 corners, or 6, or 7, or 8, you can always find a set of triangles to put it into smaller pieces. The same you can do with the non-spherical shape in 3-dimensional space, and like a pyramid or so. You can find a set of tetrahedrons like this. Can you see? Tetrahedrons, they have 4 sides. Each side is a triangle, and then you can find a set of them, put in any other shape. And then you can put the integration instead of the points into these tetrahedrons, and the number of k points, then split that space into smaller pieces, and the result becomes pretty accurate, because you can apply some math there to get results that are more precise, basically. K point, more than one K point in each direction for this method. So if you have an isolated system like a molecule, you can't do it. And to use this method to full extent, you actually need a large number of K points too, right? Because otherwise it doesn't gain anything from the math behind it. And then the integration with the smearing, Fermi or Gaussian is much faster. So meanwhile, I will copy paste my input for the lithium DOS of the 2x2 unit cell into Google Drive, right? So you can compare what you have and what I have, and then maybe see where's the difference too. But your lattice vectors should be the same, should have all the same length, right? Right? So at least the ratio is the same. So you can start with 999, but you need to do your own testing, right? You need to see if for the primitive, for the supercell based on the primitive unit cell, the K-point convergence is achieved too, right? Always do your own testing, right? So, but first try to get it run with 999. You already should get a decent result. Good enough. So where does the pixel end? How many atoms do you have? Second? How many bands do you have? And you run it in the... You didn't submit it to Q, right?
Oh, so
You run it on 4 CPUs, right? Yeah. Well, you will be roughly 3 times faster if you submit it to Q, right? But you need to wait until my calculation is finished now. So it's finished now. So pretty, you know? So that is now my density of state with 21, 21, 21 k-points. Good? It's getting better and better, doesn't it? Let's take a look at the equivalent with 13, 13, 13. Take the other back. So I guess 21, 21, 21 is either sufficient or more than sufficient, because it doesn't get much smoother than this anymore, right? Smooth, so that is very nice. And now we see right, square root behavior here until that region, and then more complicated electron interaction may change that a bit. The next part is I would increase the number of bands so that I get something that is more complete after the Fermi energy, and then I would be done. Now what do we learn from that is we need to converge the DOS with respect to k-points. The number of k-points we need to converge the DOS is much larger than for other properties like structure and total energy. So we have different convergence values for different properties. Good. So the next part we should talk about is the band structure.